Fade in on the interior of the Bridgeport Ironworks foundry, November 1887. The reverberatory furnace dominates the casting floor, a brick cathedral of industry, 20 feet long and 12 feet wide, its arched roof glowing dull orange in the pre-dawn darkness. The air thrums with heat. Workers move like shadows against the furnace light, their faces slick, with sweat despite the autumn cold seeping through the roof vents. Inside the firebox, coal burns at 1800 degrees. The flame should rise straight up, pulled by the chimney draft into the flue system overhead. It always has. For 3 years, this furnace has melted iron with perfect uniformity, the fire climbing vertically through the grate, spreading heat evenly across the reverberatory chamber where pig iron waits to liquefy. But tonight, the flame leans. Foreman William Gatties notices it first. He's standing at the charging door, about to add coal, when he sees the fire inside the box pulling hard to the left, not flickering, not wavering, but leaning like a tree bent by wind. The entire column of combustion tilts at perhaps 15 degrees off vertical, pressing against the left wall of the firebox. The roar changes pitch, deeper. The bricks on that side glow brighter. Gatties steps back. He's run this furnace for 18 months. Fire doesn't lean sideways. Fire rises. He calls over his shoulder to the night crew. Check the dampers. Something's pulling wrong. 2 men climb the iron ladder to the flue inspection platform. The dampers are open. The chimney draft sounds normal, that deep, hollow pull of air being consumed upward. But when they look down through the observation port into the firebox, they see it too. The flame is bent, solidly, continuously. Like the laws of combustion have shifted 5 degrees west, the furnace keeps burning. The iron in the reverberatory chamber begins to melt, but not evenly. The left side of the bath heats faster. Metal near the right wall stays sluggish, thick. Gatties watches the temperature differential through the inspection glass. This will ruin the pour. Uneven heat means uneven composition. Inclusions, weakness in the casting. He reduces the coal feed. The flame intensity drops, but the lean doesn't correct. He opens the secondary air vents on the right side, trying to balance the combustion. The flame remains tilted. The left wall bricks begin to tick, a sound like fingernails on stone, the noise of thermal expansion happening too fast in one place. By the time the morning shift arrives, the sideways fire has been burning for 4 hours. The night foreman has logged it. The day superintendent, Arthur Hollies, stands in front of the furnace with his arms crossed, watching orange light press against brick that was never designed to take direct flame contact for this long. He doesn't speak. He's calculating. How many hours until that wall fails? How much production they'll lose if they have to shut down for repairs? The flame roars, leaning left, defying the vertical pull of the chimney 30 feet above. The sideways fire doesn't stop. Over the next 6 days, it becomes the furnace's new behavior. Every firing, every shift, the flame tilts to the left. The workers adjust. They learn to compensate, adding more coal on the right side, adjusting air intake, rotating the charging schedule to try and balance the heat. It doesn't work. The fire wants to lean. It insists. The effects accumulate. The left wall of the firebox begins to show heat damage. Bricks that should last 2 years are crumbling after 2 weeks. The mortar between them softens, turns to powder. During the day shift on November 9th, a brick falls out of the lower left wall, just drops into the ash pit with a muffled crack. The workers stop. They stare at the gap. Behind it, the next layer of brick glows white. Tooling starts to warp. The iron rakes they use to distribute coal across the Great Bend when left too long on the left side. The wooden handles of the charging tools char faster. Men assigned to the left side of the furnace complain of the heat. It's noticeably more intense, like standing next to a different furnace entirely. The temperature 15 feet from the left wall measures 30 degrees hotter than the same distance from the right. Pours begin to fail. On November 11th, a casting for a locomotive wheel comes out with a visible grain structure mismatch. The left side dense and fine, the right side coarse. It cracks during cooling. On the 13th, a batch of tool steel shows inclusions on one side, microscopic pockets of impurity that shouldn't exist in a properly mixed melt. The quality inspector rejects the batch. The foundry loses 2 days of production. Superintendent Hollies orders the furnace shut down for inspection. The crew lets the fire die, waits 12 hours for the bricks to cool enough to approach. They crawl inside the firebox with lanterns and pry bars, checking every course of masonry. They find heat damage on the left, but no blockages, no cracks that would divert airflow. The grate is intact. The ash pit is clear. The flue system, inspected from the chimney down, shows no obstructions. They relight the furnace on November 15th. Within an hour, the flame leans left again. The workers start talking, quietly during meal breaks, away from the foreman. Something is wrong with the furnace. Not broken, wrong. Old Pavel, who has worked foundry since the 1860s, says he saw a furnace in Pennsylvania that burned crooked once. They tore it down, rebuilt it from scratch. Some said the ground underneath had shifted. Others said the chimney had been built wrong and the draft never ran true. Gatties doesn't believe in furnace curses, but he starts logging everything. Time of day when the lean is worst. Wind, direction, barometric pressure. Temperature readings at 6 points around the firebox. He's looking for a pattern inside the pattern. The flame leans left, yes, but when is it worse? When does it ease? He finds that the lean intensifies in the afternoon. Between 2 and 5 o'clock, the fire tilts almost 20 degrees. In the early morning hours, it's closer to 10. The differential isn't random. It's rhythmic, predictable, like something outside the furnace is influencing what happens inside. On November 18th, the sound changes. The roar of the fire develops a new tone, a low pulsing almost below hearing. You feel it more than hear it, a pressure that cycles every few seconds. Thrum, thrum. The workers notice it in their chests. Some complain of headaches. The flame keeps leaning. The left wall keeps glowing. The furnace continues to burn wrong. November 20th, morning shift. The left wall of the firebox is no longer intact. 3 bricks have fallen since the last inspection. The refractory lining behind them, a layer of fire clay meant to insulate the outer masonry, is exposed and crumbling. The superintendent calls in a mason. The mason looks at the damage, looks at the furnace in operation, and shakes his head. That wall's taking flame it shouldn't, he says. Direct contact. Continuous. You keep running this, you'll burn through to the outer shell in a week. Hollies asks if they can patch it. The mason says yes, but not while it's firing. They'll need to shut down, let it cool, rebuild the inner course and reline it. 3 days minimum. Hollies calculates the cost. Production halted. Contracts delayed. The foundry has orders backed up through January. He tells the mason to come back next week. They'll patch it then. The flame keeps leaning. The pressure pulses get stronger. Workers on the casting floor feel it now, a rhythmic compression in the air, like the foundry itself is breathing. Ash in the ash pit no longer settles evenly. It piles against the left wall, blown there by some internal current. The right side of the grate stays cleaner than it should. Coal fragments scatter left. Everything inside the firebox drifts in one direction. On November 22nd, the sound of the fire changes pitch again. Higher now, a whine underneath the roar. It reminds Gatties of wind through a cracked window, that thin, oscillating note that comes from air forced through a gap. But there's no gap. They've checked. The firebox is sealed. The flue is clear. The chimney draws steadily. Temperature readings confirm what the workers already feel. The left wall interior is reaching 2,000 degrees in spots, 200 degrees hotter than the design maximum. The outer masonry, 3 feet thick, is warm to the touch on the outside. You can feel the heat radiating through brick that should be insulating. At night, the left side of the furnace glows faintly red in the darkness. A casting rod left leaning against the left wall for 20 minutes warps into a curve. A water bucket placed 6 feet away begins to steam. The heat is no longer contained inside the firebox. It's leaking outward, concentrated, uneven. The right side of the furnace remains normal, cool enough to touch. The temperature difference across 12 feet of space is over 300 degrees. On November 24th, during the evening shift, a section of the left wall collapses inward. Not bricks falling, a whole section, perhaps 2 feet square, slumping into the firebox like melted wax. The workers evacuate. The furnace is still lit. They watch from the casting floor as the collapsed section glows white, then orange, then settles into the ash bed. The flame, now partially exposed through the gap, leans even harder to the left. It's almost horizontal at the base, only rising vertically in the upper third of the firebox. Hollies orders an emergency shutdown. They flood the firebox with water. Steam explodes upward through the flue. The sudden cooling cracks 4 more bricks. By midnight, the furnace is cold and half the left wall is rubble. The foundry stops production. The theories start immediately. On the casting floor in the tool room over lunch, the workers try to explain what they've seen. Fire doesn't lean sideways for 3 weeks without a cause. Something is making it happen, something physical, mechanical, findable. The first theory, a blocked flue. Maybe soot has built up inside the chimney system, creating uneven draft. Air pulls harder on one side, dragging the flame sideways. Holly's orders a full flue inspection. They lower a man on a rope into the chimney from the top. He scrapes the walls, checks for buildup. The flue is clear. Some soot, normal for 3 years of operation, but nothing that would block airflow. The draft measures strong and even. The chimney is not the problem. Second theory, the grate. Maybe the cast iron grate that holds the coal has warped from heat, creating an uneven bed. Coal piled higher on one side would burn hotter there, pulling the flame. They remove the grate. It's flat. No warping. The mounting brackets are intact. They install a new grate anyway. When they relight the furnace on November 27th, the flame leans left within 30 minutes. Third theory, external airflow. Maybe wind from outside is somehow entering the firebox, pushing the flame sideways. It's November in Connecticut. Strong winds are common. They check every door, every vent, every seam in the masonry. Everything is sealed. They run the furnace with all vents closed except the primary air intake. The flame still leans. They try firing on a dead calm day. No wind, barometric pressure high and stable. The flame leans. Fourth theory, whispered more than spoken, sabotage. Someone has tampered with the furnace. A disgruntled worker, maybe. A competitor trying to ruin the foundry's reputation. They search for evidence. Hidden vents, drilled holes, anything that would let someone manipulate the airflow from outside. They find nothing. The furnace is intact. The masonry is solid. No one has sabotaged anything. The engineers from the foundry's main office arrive on November 29th. 2 men, both trained in combustion systems. They bring instruments, manometers to measure pressure, pyrometers for precise temperature, anemometers to check airflow. They spend 2 days measuring everything. Draft velocity in the flue, air pressure at the grate, temperature at 20 points inside the firebox, oxygen content in the exhaust. They find asymmetries. The pressure at the left side of the grate is measurably lower than the right, just a fraction of an inch of water column, but consistent. The airflow entering the firebox shows a bias. More air enters from the right side of the intake, flows across the grate, and exits to the left. The temperature in the upper firebox is stratified, hot layers above cool layers, not mixing as they should. But they can't explain why. Nothing in the furnace design accounts for it. The intake is centered. The grate is level. The flue should pull evenly. One of the engineers suggests demolishing the furnace and rebuilding it. Start over. Correct whatever hidden flaw is causing this. Holly's refuses. Demolition and reconstruction would take 8 weeks. The foundry can't afford it. On December 1st, they attempt a firing with modified air intake. They block half the primary air vent, forcing all combustion air to enter from one side. The flame leans the opposite direction for 10 minutes, then slowly shifts back to the left. Whatever is pulling the fire sideways is stronger than their adjustments. The workers are nervous now. 3 weeks of a malfunctioning furnace, theories that lead nowhere, a machine that refuses to behave according to known principles. Old Pavel says it again, tear it down. Some furnaces are wrong from the start. You can't fix wrong. You can only rebuild. But Gattis keeps logging, time of day, wind speed and direction, outside temperature, barometric pressure. He's filling notebooks with data, looking for the variable that correlates with the flame's behavior. He doesn't believe the furnace is cursed. He believes they're missing something, something observable, measurable, physical. On December 3rd, he finds the first clue. The flame leans hardest when the wind outside is from the northwest. Not inside the building, outside, hitting the chimney. On calm days, the lean is milder. On days with strong northwest wind, the flame tilts 20 degrees or more. There's a connection, something about the wind, something about the chimney. Something they haven't measured yet. December 5th. The furnace is cold. Hollies has authorized one more round of investigation before committing to demolition. Gatties and the two engineers stand inside the empty firebox with lanterns, looking for anything they might have missed. The left wall has been temporarily patched with fire clay. The grate has been cleaned and relevelled. Everything is as correct as they can make it. Gatties lights a cigarette. He's not supposed to smoke inside the firebox, but the furnace is cold and he's exhausted. He exhales. The smoke drifts, not upward toward the flue, sideways, to the left, slowly but visibly. The engineers stop talking. They watch the smoke. There's no fire, no heat, no draft, but the air inside the firebox is moving laterally. One of the engineers lights a match, holds it steady. The flame leans left, just slightly, barely perceptible, but it's there. Air is moving inside the firebox even when the furnace is unlit. A current, a bias. Something is making the air flow sideways before combustion even starts. They bring in smoke candles, the kind used to test ventilation systems. They light one in the center of the grate. The smoke rises initially, then curls to the left as it climbs, drawn by some invisible current. They light another at the right side of the firebox. That smoke crosses the space, moving left before rising into the flue. The airflow inside the chamber is not vertical. It's helical, spiraling, asymmetric. Gatties climbs out of the firebox and goes outside. The foundry building is large, 100 feet long, 60 feet wide, with the furnace positioned near the center. The chimney rises from the furnace to the roof, then extends another 20 feet into the open air. It's built of brick, 14 inches square, with a damper at the base and a rain cap at the top. He walks around the chimney exterior. The wind today is light from the northwest. He wets his finger, holds it up. The air is moving but gently. He looks up at the chimney top. The rain cap is asymmetric, a simple sheet metal cover mounted slightly off-center. He's never noticed before. Why would he? Rain caps don't affect draft. They just keep water out. But this one is mounted so the overhang is longer on the southeast side. When wind hits from the northwest, it strikes the cap, deflects downward along the longer side, and creates a low-pressure zone on that side of the chimney opening. Not much. Not enough to reverse the draft, but enough, maybe, to bias it, to pull harder on one side of the flue than the other. He goes back inside, tells the engineers. They're skeptical. A rain cap can't cause this, but they agree to test it. They climb to the roof, remove the cap entirely, and expose the bare chimney opening. They light the furnace. The flame leans left, less than before, but still leaning. The rain cap was part of it, but not all of it. December 7th. They conduct pressure measurements at multiple heights inside the chimney. At the base, the draft is even. At 10 feet up, it begins to diverge. The left side of the flue shows slightly lower pressure, meaning air is being pulled harder there. At 20 feet, the difference is measurable. At the top, where the chimney emerges into open air, the wind is creating a shear effect. The external airflow across the chimney opening is not uniform. Wind from the northwest creates a low-pressure zone on the southeast side of the opening, pulling exhaust gases preferentially from that side of the flue, which means the draft inside the furnace is asymmetric. Air is being pulled harder from the left side of the firebox because the chimney is pulling harder on the left side of the flue. The fire leans toward the path of least resistance, toward the stronger draft. But that's not enough to explain what they've seen. The lean is too pronounced. The heat concentration too extreme. There's more happening inside the firebox than just draft bias. They bring in ash from the last firing. It's piled in the ash pit, 3 days cold. They sift through it. The ash from the left side is finer, smaller particles, more completely combusted. The ash from the right side is coarser, with larger coal fragments. Incomplete combustion on the right, more complete on the left. The fire has been burning hotter and longer on the left side, not just leaning there. Gatties places his hand on the outer wall of the furnace. Still warm. The left side is warmer than the right, even 3 days after shutdown. The brick has absorbed heat unevenly. Thermal mass, saturated asymmetrically. He remembers something from his apprenticeship. Hot masonry radiates heat inward as well as outward. If the left wall has been consistently hotter for 3 weeks, it's been radiating more heat back into the firebox, creating a feedback loop. Hotter wall, right arrow, more radiant heat, right arrow, hotter combustion, right arrow, hotter wall. One of the engineers kneels by the air intake. He's measuring the pressure differential again, but this time he's thinking about why it exits. The intake is at floor level. The firebox is elevated on a foundation. Air enters from below, passes through the grate, and feeds the fire. But if the draft is pulling harder on the left side of the firebox, then air will preferentially flow toward that side as it enters. It will cross the grate laterally before rising. The entire combustion zone will shift left. And if the combustion shifts left, the heat shifts left. And if the heat shifts left, the wall temperature rises. And if the wall temperature rises, the radiant feedback intensifies. And if the radiant feedback intensifies, the combustion shifts further left. It's a cycle, self-reinforcing, started by a small bias, amplified by thermal feedback, sustained by continued operation. The furnace has been training itself to burn sideways for 3 weeks. On December 9th, they hear it, the pulsing sound, the low-frequency thrumming. Gattis is standing near the furnace during a test firing when he feels it in his chest. He puts his hand on the outer wall. The brick is vibrating, very slightly, rhythmically. He listens. The pulse matches the cycling of the flame, a surge, a pause, a surge. The fire is oscillating, not visibly, but acoustically. Pressure waves inside the firebox, resonating at a frequency determined by the chamber dimensions. Resonance. The furnace is resonating. The asymmetric draft is creating pressure waves that reflect off the walls and reinforce at a specific frequency. And that resonance is biasing the airflow even further, pushing combustion air toward the left, sustaining the lean, amplifying it. It's not one thing, it's 4 things. Wind shear at the chimney, draft bias in the flue, thermal feedback from the wall, acoustic resonance in the chamber, all working together, all reinforcing each other. They finally understand what they're fighting. December 10th. The engineers present their findings to Superintendent Hollies. They've mapped the problem. Now they need to prove their hypothesis and design a solution. Hollies listens, arms crossed, skeptical. They're telling him that wind he can barely feel outside is bending fire inside a sealed furnace. That brick walls are feeding heat back into combustion, that the firebox is resonating like an organ pipe. It sounds like theory. He wants proof. They set up the test. First, they need to confirm the wind shear effect. They build a temporary extension for the chimney, a sheet metal collar that rises another 5 feet and includes a symmetrical cap design. The goal is to eliminate the low-pressure zone created by northwest winds. They install it on December 11th. The wind that day is light, variable. They wait. December 12th brings steady northwest wind at 12 miles per hour, perfect test conditions. They light the furnace at dawn. The flame rises vertically for the first time in a month. No lean, no bias. The fire climbs straight up through the grate, spreads evenly across the reverberatory chamber. The workers stop and stare. It's burning correctly. But 2 hours into the firing, the flame begins to drift left again. Not as pronounced as before, maybe 5 degrees instead of 20, but still present. The chimney modification helped. It didn't solve the problem. The engineers expected this. The wind shear was the initiating factor, but the thermal feedback and resonance are now self-sustaining. The furnace has been conditioned to burn sideways. The left wall is saturated with heat. The acoustic modes are established. Fixing the chimney draft stops the external forcing, but the internal dynamics remain. Next test, break the thermal feedback. They need to cool the left wall, reduce the radiant heat, interrupt the cycle. But they can't do that while firing. The wall needs to dissipate heat over days, not hours. Hollies authorizes a 3-day shutdown. They let the furnace go completely cold. They open all inspection doors, ventilate the firebox, let December air circulate through the chamber. On December 15th, they measure the wall temperature. The left side has cooled, but it's still 10 degrees warmer than the right. The brick holds heat tenaciously. They use water carefully to avoid thermal shock to cool the left wall further. They monitor it for 24 hours. By December 16th, the temperature differential is less than 3 degrees. They relight the furnace with the modified chimney cap in place. The flame rises vertically. 1 hour passes, still vertical. 2 hours. The flame wavers slightly but doesn't commit to a lean. 3 hours. A slight drift to the left, barely 5 degrees. By the 4th hour, it stabilizes at 8 degrees off vertical. Better, not perfect. The engineers confer. The thermal feedback is broken, but the resonance remains. The chamber dimensions, the grate spacing, the flue opening, all of these create natural frequencies where pressure waves can build. When the draft pulls asymmetrically, even slightly, the resonance amplifies that asymmetry. They need to disrupt the acoustic modes. They try baffles, metal plates inserted into the firebox at strategic points to scatter the pressure waves. The baffles warp from heat after 30 minutes. They try changing the air intake configuration, adding secondary vents to create turbulence. The turbulence helps slightly. The lean drops to 5 degrees. On December 18th, they try the final modification, a draft splitter in the flue. A vertical plate mounted at the base of the chimney, dividing the flue into 2 equal channels. The idea is to force symmetric flow. Each channel pulls half the exhaust, preventing one side from dominating. It's crude, but it might work. They install it in 4 hours. They light the furnace at noon. The flame rises vertically. It stays vertical through the afternoon. That evening, with northwest wind at 15 miles per hour, the flame remains centered. Temperature readings show even heat distribution. The reverberatory chamber melts iron uniformly. By midnight, they've completed a full firing cycle with no lean. Gatties checks the left wall, warm but not hot, no excessive glow, no ticking. The brick is holding steady. He checks the ash pit. Ash is settling evenly across the grate, no lateral drift. He listens. The roar is smooth, no pulsing, no oscillation. The furnace sounds like it did a year ago. The engineers document everything. The initiating cause was wind shear at the chimney, creating draft bias. The amplifying factors were thermal feedback from the overheated wall and acoustic resonance in the firebox. The solution required 3 interventions: symmetric chimney cap, thermal reset of the masonry, and draft splitting in the flue. No single fix worked alone. The system was too coupled, too reinforcing. On December 20th, Hollies authorizes full production restart. The furnace runs continuously for 5 days with no issues. The flame burns vertically. The iron melts evenly. Castings come out uniform, strong, free of defects. The sideways fire is gone. The workers don't talk about it much after that. They've seen a machine behave in ways it shouldn't. They've seen fire bend to forces they couldn't see. They've learned that furnaces, like all things built by men, can develop their own behaviors, emergent, complex, resistant to simple fixes. Old Pavel, asked what he thinks finally solved it, shrugs. You stopped fighting the furnace, he says. You listened to it instead. The case of the Bridgeport Iron Works furnace, documented in December 1887, represents a convergence of 4 distinct mechanical phenomena acting in concert to produce a single, dramatic effect: sustained lateral deflection of a vertical flame. The initiating mechanism was wind shear at the chimney terminus. The foundry's chimney extended 20 feet above the roofline, exposing it to prevailing northwest winds. The asymmetric rain cap, with its longer overhang on the southeast side, created a low-pressure zone when struck by these winds. This zone preferentially pulled exhaust gases from the left side of the flue system, establishing a draft bias. The bias was small, measured at less than 0.05 inches of water column, but persistent and directional. This draft asymmetry created a lateral pressure gradient inside the firebox. Air entering through the primary intake at the base of the furnace experienced unequal resistance paths. The path toward the left side of the firebox, where draft was stronger, offered lower resistance than the path toward the right. Combustion air, following the gradient, flowed laterally across the grate before rising. This shifted the primary combustion zone approximately 8 inches to the left of the firebox centerline. The lateral shift in combustion concentrated heat against the left wall. Refractory brick, designed to withstand high temperatures, absorbs thermal energy and re-radiates it into the chamber. As the left wall heated beyond design parameters over multiple firing cycles, it began radiating more energy back into the firebox than the right wall. This radiant asymmetry further intensified combustion on the left side. The system entered a positive feedback loop. Lateral combustion heated the left wall, which radiated heat that intensified lateral combustion. The third factor was thermal stratification. Large furnaces develop distinct temperature layers. Hot gases rise and accumulate at the top, cooler gases settle below. In a symmetrically firing furnace, this stratification is horizontal. In the Bridgeport furnace, the lateral heat concentration created tilted thermal layers. Hot gas layers sloped from upper left to lower right. These tilted layers altered buoyancy forces inside the chamber, creating additional lateral flow components that reinforced the original draft bias. The fourth mechanism was acoustic resonance. The firebox dimensions, 20 feet long, 12 feet wide, 8 feet high, created natural resonant frequencies in the pressure field. When combustion fluctuations occurred at or near these frequencies, pressure waves reflected off the chamber walls and reinforced. The asymmetric draft bias meant these resonant modes were not centered in the chamber, they concentrated on the left side. The resonance acted as an amplifier, converting small pressure fluctuations into significant airflow biases. Workers felt this as the rhythmic pulsing that developed in the final week before shutdown. The solution required interrupting all four mechanisms. The modified chimney cap eliminated wind-induced draft bias. The 3-day cooling period broke the thermal feedback by allowing the left wall to dissipate its stored heat. The draft splitter in the flue forced symmetric exhaust flow, preventing the re-establishment of lateral pressure gradients. And the secondary air vents introduced turbulence that disrupted the acoustic modes, preventing resonant amplification. What makes this case significant is not the individual phenomena. Each was understood in 1887, but their interaction. The system was coupled. Wind shear alone would not have produced a 20-degree flame deflection. Thermal feedback alone would not have sustained it for 3 weeks. Resonance alone would not have created the pressure pulses. But together, each mechanism reinforced the others. The furnace became a system with emergent behavior that none of its components, acting independently, could produce. This is the nature of complex mechanical systems. They couple, they feedback, they amplify small inputs into large outputs through iteration and reinforcement. The Bridgeport furnace was not malfunctioning in the traditional sense. No component was broken. It was behaving according to physical law. But those laws, acting in concert, produced behavior that appeared to violate the principles of combustion. The workers who watched the flame lean sideways night after night were not witnessing magic. They were witnessing physics, lateral pressure gradients, asymmetric draft from external wind shear, thermal stratification inside a large chamber, resonance-induced airflow bias, partial draft collapse on one flue wall, masonry heat saturation causing flow deflection, all of it measurable, all of it explainable, all of it obeying the same laws that govern every fire ever lit. But understanding those laws and predicting their interaction are different tasks. The engineers solved the problem not by calculation, but by observation and iteration. They measured what the furnace was doing. They formed hypotheses. They tested interventions. They failed. They tried again. The solution emerged from engagement with the physical system, not from theory applied in abstraction. This is how engineering advances, not through sudden insight, but through patient observation of machines that refuse to behave as expected. The Bridgeport furnace taught its operators that fire, confined and forced to burn under artificial conditions, can develop its own tendencies, its own preferences, its own emergent dynamics that resist simple correction. The lesson recorded in William Gatti's notebooks, now archived at the Connecticut Industrial Museum, is simple. When a machine behaves strangely, it is not rebelling, it is teaching. The flame that pulled sideways was not an aberration. It was a demonstration of coupling, of feedback, of resonance, of the complex ways that simple forces combine to produce unexpected results. The furnace burned straight after December 20th, 1887. But the men who ran it never forgot the 3 weeks when fire, bound by brick and forced by draft, chose its own direction and leaned.